Okay, hi, this is question number 2 from the related rates worksheet, the one that says easy, and I think it says goes with card game. Again, if you haven't looked at the related rates cards and the lesson from, I think, April 8th, you should look at that before you do these. Okay, question number 2. We have a 15-foot ladder that is resting against a wall. The bottom is initially 10 feet away from the wall, and it's being pushed toward the wall. And here's our first rate at a rate of 1/4 foot per second. How fast is the top of the ladder moving up the wall 12 seconds after we start? So when we draw the picture, we want to usually draw the things that are the same no matter uh, what part of the problem that we're in. So I'm going to draw a ladder against a wall, and these we almost always use X and Y when we're in like a Pythagorean place. So this would be X down here. And then the ladder, we'll call the ladder S. That's just, we use X, Y, and S a lot for Pythagorean theorem problems. Now, in our drawing, one thing that we can say is that the ladder is 15 feet. And well, the length of the ladder isn't going to change. So that's like definitely a given. And that means the hypotenuse of this triangle is not going to change. And so we know that we're going to have like an x squared plus y squared equals s squared situation. But let's fill in a little bit more of what we know. I mean, they tell us that the bottom is initially 10 feet away from the wall, but that's just an initial condition. That's not the same for the whole problem. So I'm not going to put that 10 feet on here. It does say that the ladder is being pushed toward the wall at a rate of 1/4 foot per second. Okay, so there's a rate, and that's going to be the same the whole problem. It tells us that's the rate. It doesn't say sometimes that's the rate. So what I'm going to say is the bottom of the ladder moving this way would be, that rate would be called dx dt, right? Because that's basically your delta x, or how the rate that the x is changing. And that is 1/4, what units are we using here? 1/4, 1/4 foot per second. And here's something tricky, but if I show you it now, you'll always remember it. Since we're moving toward the origin from the right, this is negative. Okay, so whenever you're on the x-axis and you're moving to the, left, yeah. Whenever you're on the x-axis and you're moving left, that's a negative dx dt. Okay, and then they're asking us to find how fast the ladder is moving up the wall. So I think I'm going to go ahead and mark that here. You know, as I push the bottom, the top of this ladder is going to be sliding up. So that's actually what they want us to find. And it's okay to like put that as a question mark. So basically, the only things that are the same for the whole problem are this 15-foot ladder and this rate. There are other pieces of information we're going to use, but those are our givens. So then the second thing we're going to fill in is our givens. So we have the given that S equals 15, right? That's the length of the ladder. And that dx dt equals negative 1/4 feet per second. And I'm going to go ahead and do this by hand and switch to calculator only if I need to. Okay, and then the next thing we're supposed to say is what are we supposed to find and under what conditions? So this is really important. Under what conditions? So it said that it wants us to find how fast is the top of the ladder moving up the wall. So we're supposed to find dy dt. How fast is this ladder sliding up the wall? But dy dt is always changing, so they must tell us what the conditions are. Find dy dt when t equals 12. And one thing I thought about that was, but we've never seen a t in the problem. Like, we're using it as, with relationship to time. So I'm like, all right, I'm going to need a dy dt, but how am I going to play with that 12 seconds so that it matches? Right? If you have a right triangle, most of the time, you're going to do a Pythagorean problem. So the equation that you're going to want, that equations of relationships, is going to be the x squared plus y squared equals s squared. So I'm going to do this on the whiteboard. Hopefully I don't mess up my markers. So here's my equation. X squared plus y squared equals s squared. Actually, I don't know why I didn't write it the other way. I'll do it this way. S squared equals x squared plus y squared. We know that s is always 15. So let's just go ahead and put that in now. I mean, we can put it in later, but it's just as easy to do it now. And so I'm ready to take a derivative. This is going to have a derivative of 0 because it's a constant. So when I take my derivative, I get 2x dx dt, 2y dy dt. Now, every now and then, a student says, hey, when we learned implicit differentiation, you said that we don't have to write dx dt. Right. When we're doing explicit differentiation and it's not a word problem, we don't write dx dt because those are dy dx problems. So those are different. So don't worry about that. That rule still applies. But in related rates problems, no matter what the variable is, we do the dy dt, dx dt, whatever it is. Okay, so one thing I can do here is I can divide everything by 2. That'll make my life a little easier. So let's divide everything by 2. And then we are trying to find dy dt, so let's solve for dy dt. And you can do that really on your own if you want. And I'll give you a second to do that, so maybe pause. So eventually, and again, if you didn't do that algebra on your own, you should pause and do that. You get, it's like negative x over y dx dt. So, and I just did algebra to get to here. So we could plug in now because we have dx dt, right? So that's good. We're trying to find dy dt. Well, we know dx dt is negative 1/4. I'm going to leave units out for the moment. Negative 1/4 feet per second. But like, what about the x and y? Because we're ready to solve now because we have our derivative. But what about x and y? Like, that would actually mean when we're talking about x and y, we're actually talking about linear distance. So x and y. So how can we find x and y? Well, now it's time to look at these other conditions, okay? So they told us that we're supposed to find this when t equals 12 seconds. So another question we have to answer is, now we know we need to know what is x and y when t equals 12 seconds. Okay, so these are often like puzzles. So what is x and y when t equals 12 seconds? Well, what do we know? We know that x is moving and getting smaller by 1/4 foot per second. That doesn't help us unless we know what x was to start with. And we do. In the original problem, it did say the bottom is initially 10 feet away from the wall. So when we started, the bottom of the ladder was 10 feet away. Now it's been moving this way at negative 1/4 foot per second for 12 seconds. You're like, I never would have thought of this. It's okay. Now that you've seen it once, you'll know to use like, they must have given you enough information to do what you need to do. So originally, the bottom was 10 feet away. They're curious about what the situation is after 12 seconds. So after 12 seconds, this ladder has slid, right, at a quarter per second. So it's sliding this way. And if it moves 1/4 foot per second for 12 seconds, I mean, you can do a lot of fancy math on this, but hopefully you know that it's moved 3 feet, right? And just 12 times -1/4. And we're going to call that -3 feet, right? So it has moved -3 feet. So if it's moved -3 feet, that means it's now 7 feet from the wall. Okay, and if that's messing with your brain a little bit, then take a second and maybe redo that logic yourself, okay? So we went from 12 feet, we moved 10 feet, we moved for 12 seconds at this rate, which means we moved -3 feet, which now means the X value is 7 feet. So what's the Y value? Well, guess what? At this particular time, at 12 seconds, we know X is 7 and Y is 15. So I can go ahead and solve that. I can just use Pythag here. So I have 225, because that's 15 squared, equals X squared, which is 7 squared, plus Y squared. And again, I'm doing as much as I can without a calculator at first. So then I get basically, after I do a little math, -49 minus 49, Y squared equals 176. So that means Y equals root 176. Okay, so what we have just discovered is that at this 12 seconds, X would be 7 feet and Y would be, like, this height right here would be square root of 176. And if you want like a number to go with that, what's the closest? Like 13 squared is 169. So we basically have a triangle that's like 7 by 13 point something by 15. Now we know what we need to plug in. Because remember, when we were looking at this, oh, I knew that would happen. When we were looking at this, we got all the way down here, but we needed an X and a Y. Remember I told you originally, like, hey, there's no actual T here. But now I know my negative X and Y. So X ended up being 7. So this is going to end up being -7. Again, I'm going to skip units for a minute. Y ends up being root 176 and times -1/4. So one thing I like to do is do a lot of this math. Like, I don't want to do square root of 176 until the end, because I don't want to have to round it until the end. Negative times a negative, so I end up with a positive 7/4 root 176. And then you can put that in your calculator. Don't forget to use parentheses in the numerator when you put it in your calculator. And remember, for AP Calc, we want 3 decimals, and we get 0.131. We're going to go back and do units in a second. So what was I looking for? I was looking for the rate that the ladder is moving on the y-axis. Does it make sense that I got a positive answer? It does, because as the bottom of the ladder moves closer, the top of the ladder is moving up, so that will give us a positive y value. I did 3 decimal points. So let's do some units here for a minute. X is linear, right? It's just the distance, so that would be feet. Y would be feet, because remember, those numbers represent at this moment. This is 7 feet. This is root 176, which is 13 point something feet. And then this -1/4, that was the rate of change here. So that's feet per second. So we want to think what did we want this units to end up being? In a perfect world, this unit ends up being feet per second, right? Because as we move up the y-axis, that's feet per second. And we can see that that's going to work out fine, right? That cancels, or you can say those 2 feet cancel, and you end up with feet per second. Again, you don't have to do units when you show your work on these problems. If you already know dy dt is going to be feet per second because you're moving up, it's not going to be squared because it's not area. It's not going to be cubed because it's not volume. It's just a linear motion. And whenever you have a linear motion, it's going to be like feet per second or miles per hour. And that is the answer to the problem. I'd like to encourage you to try this one 100% by yourself and see if you could get the same answers.